Hello friends, my name is Diganjit Rawal, ME Mechanical Design Engineering, lecturer in Automobile Engineering, Government Polytechnic Nashik. Uh, I am explaining the details about derivation of on stability of vehicle on slope in the directional stability part 4a. In the previous part, I have explained the theoretical information regarding stability of vehicle on slope as well as stability of vehicle on turn. So, why the necessity to study the derivation for stability of vehicle on slope? So, these are the figures, different types of slopes, and the vehicle is moving from that slope. So, driving safely can be achieved by the prevention of risky situations like vehicle is on the slope or is on the turn, which may require the knowledge of vehicle dynamic state as well as the road geometry. It is thus essential for designer to have in real time a good estimation of the related variables and parameters. So what is mean by that? To avoid, to prevent from risky situations like vehicle on slope. So we have to derive this equation. We have to learn the stability of vehicle on slope. Next, which may require the knowledge of vehicle dynamic state as well as the road geometry. So we have to study the road geometry. What are the types of roads? What are the what are the slopes? What are the inclinations of the road? As well as we have to study the forces acting on the vehicle, movements acting on the vehicle to study the stability of vehicle on slope. Next, so here is the figure which shows that forces acting on a vehicle at rest on an inclined plane or slope. So let the vehicle rest on a slope of inclination theta to horizontal. This alters the distribution of the weight between the front and the back axle, that is rear axle, and gives rise to reaction which can have components along the perpendicular to the inclined plane as shown in figure. So CG is the center of gravity of vehicle, theta is the angle of inclination plane in degree. So in this figure, F is the point at point of contact at front wheel, R is the point of contact at the rear wheel. So FF and FR are the horizontal forces and RF and RR are the vertical forces. So weight of the vehicle W is acting downward from the CG center of gravity of the vehicle. Next, notations. So stability of vehicle on slope. On this, the W is equal to weight of the vehicle plus weight of the driver is equal to mg in Newton. F and R are the front and rear wheel respectively. FF and FR is the horizontal or x-axis force on the front and rear wheel respectively in Newton. RF and RR are the vertical reactions on the front and rear respectively in Newton. So B is the central distance between front and rear wheel in meter. H is the height vertical distance of the CG from ground in meter. L is the horizontal distance between CG and center of rear wheel in meter. B minus L is equal to horizontal distance between CG and center of front wheel in meter. So these are the notations required to derive stability of vehicle on slope. Next, here we resolve the weight of the vehicle into x-axis and y-axis, that is in horizontal direction and vertical direction. So W is resolved with horizontal direction, that is parallel to that inclined plane is w sine theta, and w is acting downward direction, so w cos theta is acting perpendicular to the inclined plane, and that magnitude is w cos theta. So resolving forces parallel and perpendicular to the slope for horizontal force, summation f summation h is equal to 0, that is left hand side forces is equal to right hand side forces. So here only one force is for left hand side, w sine theta, and for right hand side there are two forces, so f and fr. So we can say that summation h is equal to 0, so w sine theta is equal to ff plus fr. We say that this equation is equation number 1. Next, for vertical forces, summation v is equal to 0. So downward forces is equal to upward forces. Here the downward force is w cos theta, and the upward forces are rf plus rr. So we can write this as w cos theta is equal to rf plus rr. So we can consider this as the equation number 2. For movement at point F, summation mf is equal to 0, anticlockwise movement is equal to clockwise movement. So at point F, we consider two force from the point F, we consider the movement, and the w sine theta is giving anticlockwise movement, as well as reaction at rear wheel rr is also giving anticlockwise movement. For this perpendicular distance is, so for w sine theta the perpendicular distance from point F is h, and for rr the perpendicular distance to F is B. So we can write this movement as W sine theta into H plus RR into B. These are the anti-clockwise movement. And for clockwise movement, we can say that the force is W cos theta, and the perpendicular distance is B minus L. So we can write the movement as W cos theta into B minus L. So we consider this as the equation number 3. Next, for movement at point F, summation mf is equal to 0. We have seen this in previous slide. So we can read it as w sine theta h plus rr b is equal to w cos theta into b minus L. So we gather the theta term to the one side. So the equation becomes rrb is equal to w cos theta into b minus L minus of w sine theta into h. So to uh, find out reaction at rear wheel, we have to divide with b to the both side. So dividing b to the both side, equation becomes r is equal to w by b into cos theta into b minus L minus of w into h by b sine of theta. So here we can see that the at right hand side w by b is common. So taking w by b common, the equation becomes rr is equal to w by b into a whole bracket b minus L cos theta minus of h sin theta. So consider this equation as equation number 4. So here up till now we have find out the reaction at rear wheel. Next, so from equation 1, we know that w sine theta is equal to ff plus fr. We already know that it becomes because of summation at point summation h is equal to 0. From equation 2, we know that w cos theta is equal to rf plus rr, summation v is equal to 0. So we know that hence rf is equal to W cos theta minus RR. That equation becomes equation number 5. So putting value of RR is equal to W by B into whole bracket B minus L cos theta minus of H sin theta in equation 5. It becomes RF is equal to W cos theta minus of whole bracket W by B into B minus L cos theta minus of H sin theta. So RF is equal to W cos theta minus of, here we have multiplied each term. So W by B into B cos theta minus of W by B into L into cos theta minus of W by B into H sin theta. So we have multiplied here by W by B to the bracket. So next we see that RF is equal to W cos theta minus of W by B into B cos theta, and when we withdraw that bracket, that minus and minus becomes plus. So plus W by B into L cos theta, again minus minus get cancelled and it is plus W by B H sin theta. So next we can see that RF is equal to W cos theta minus of W cos theta, because B get cancelled, so it remains minus W cos theta plus of WL by B cos theta plus of WH by B sin of theta. So equation becomes W cos theta minus W cos theta get cancelled, so it is 0. So RF is equal to WL by B cos theta plus WH by B sin theta. So here we take the common W by B, then equation becomes RF is equal to W by B into, in bracket, L cos theta plus H sin theta. So this is the equation for RF, and previous slide we have draw the equation for RR. Next. So there are two situations for the slope. So first situation is if the angle theta is increased gradually, a situation arises when either the vehicle is about to overturn. So this is situation 1 for the vehicle on slope. So the instability due to this happens at the point when RR becomes 0. So about to overturn, then at that time RR is equal to 0. We have to consider RR is equal to 0. So RR is equal to W by B into whole bracket B minus L cos theta minus of H sin theta. We know that we find out this in previous slide. So we put the value of RR is 0. So putting 0 value, 0 is equal to W by B into whole bracket B minus L cos theta minus of H sin theta. So taking H sin theta to the left hand side and dividing by W by B. So equation becomes H sin theta is equal to B minus 1 cos theta, B minus L cos theta. So taking theta term to one side, sin theta upon cos theta is equal to B minus L upon H. So we know that sin theta upon cos theta is equal to tan theta. So equation becomes tan theta is equal to B minus L upon H. So it indicates that at the point of overturning, the line of action of the weight W passes through the contact point F. Next, so this is the situation 1 about to overturn. We have to find out tan theta is equal to B minus L upon H. Next, situation 2. In situation 2, what is the situation 2? If the angle theta is increased gradually, a situation arises when the vehicle is about to slide down the slope. So in situation 2, the vehicle is about to slide down the slope. Okay, and in situation 1, vehicle is about to overturn. So in situation 2, there are also two conditions. So first condition, condition 1, the brakes are not efficient. So what is the first condition? In situation 2, the brakes are not efficient. So condition 1, the brakes are not efficient enough to prevent the wheels from turning before slide. In this case, the limiting value of theta can be determined by the brake torque available. So we know that torque is equal to force into radius. Tf is equal to braking torques at the front wheels. Tr is equal to braking torques at the rear wheels. R is equal to radius of the wheel. So we calculate Tf and Tr as Tf is equal to Ff into R and Tr is equal to Fr into R. From equation 1, we know that W sine theta is equal to Ff plus Fr is equal to Tf plus Tr whole divided by small r. So we calculate sine theta as, we got the value of sine theta is it's equal to in bracket Tf plus Tr divided by W into R. For condition 1, brakes are not efficient. For that, we have to calculate sine theta, and that equation becomes sine theta is equal to Tf plus Tr divided by W into R. So this is the situation 2 and condition 1. Next, here the situation 2 remains same and condition is 2. So if the angle theta is increased gradually, a situation arises when the vehicle is about to slide down the slope. At that time, the condition 2 is the brakes are sufficiently powerful for the coefficient of adhesion mu to limit the sliding of the vehicle. Here, force is equal to mu into reaction. So from equation 1, we know that Ff plus Fr is equal to W sine theta. From equation 2, we know that Rf plus Rr is equal to W cos theta. But Ff plus Fr is equal to mu into Rf plus Rr. That equation becomes A. From equation 1 and 2, we can write this as Ff plus Fr is equal to mu into Rf plus Rr. We know that F is equal to mu into R. So putting equation 1 and equation 2 in equation A, W sine theta is equal to mu into W cos theta. So equating the theta terms to one side, so sine theta upon cos theta is equal to mu, because W on both sides will get cancelled, and we can say that tan theta is equal to mu, or we can calculate theta term as tan inverse of mu. So this is the situation 2, condition 2. The brakes are sufficiently powerful. At that time, we have to consider coefficient of adhesion mu, and we can calculate it as tan theta is equal to mu. So this is the condition 2 in situation 2. Next, so here we have to summarize the situation 2, the stability of vehicle on slope. In situation 2, if the angle theta is increased gradually, a situation arises when the vehicle is about to slide down the slope. So at that time, condition 1 is brakes are not efficient. Condition 2 is brakes are sufficiently powerful. So for condition 1, we have to calculate sine theta is equal to Tf plus Tr upon W into R. For condition 2, brakes are sufficiently powerful. We have to calculate tan theta is equal to mu. We have seen these equations. We have derived these equations in previous slides. So this is the summary for situation 2, and this is the comparison for situation 2 condition 1 and situation 2 condition 2. Next, here there are two situations for slope. situation 1 is theta increase gradually about to overturn, and situation 2 theta is increased gradually about to slide down the slope. So in that case, in situation 1, we have to calculate tan theta is equal to b minus L upon h, and situation 2 about to slide down the slope, we have to consider condition 1, the brakes are not efficient, and condition 2, brakes are sufficiently powerful. This is the summary, this is the comparison between the two situations, about to overturn and about to slide down the slope. And here we have summarized the complete stability of vehicle on slope. So in that slide I have given the summary regarding the situation 1 and situation 2, and in situation 2 there are two conditions, condition 1 and condition 2. So I think all of you have understood very well the concept of stability of vehicle on slope, and in the next part, that is in stability of vehicle on turn, part directional stability, uh, part 4b, we will discuss about the stability of vehicle on turn. So thank you very much. Thank you very much for your kind attention. Thanks a lot.